Hello everyone and welcome back to ECMath. Today we're going to be looking at 2.6.2, which is more about rational functions. In the last video we looked at transformations of the functions 1 over x and 1 over x squared, and we also learned how to find wholes. If you need to go back and review any of those things, I'd recommend you go back and look at the previous video. But it turns out that with rational functions, I would say most rational functions are not transformations of 1 over x or 1 over x squared. They're sort of complicated objects on their own. As a reminder, the general rational function is a ratio of two polynomials. Some numerator polynomial we usually call p of x, and a denominator polynomial we usually call q of x. So we're looking at polynomials that are in a ratio. Sometimes they come in factored form, sometimes they don't come in factored form. It kind of depends on the problem. We're going to start by graphing this one right here, y equals x minus 1 over x squared minus 2x minus 3. The first step in graphing a rational function like this is deciding what the end behavior will be. That is, as x gets very large or very small, what's going to happen. And the way you do that is you compare the degrees of the numerator polynomial to the denominator polynomial. So in this case, x minus 1 is a polynomial of degree 1, and x squared minus 2x minus 3 has an x squared in it, so that's a polynomial of degree 2. We're basically only looking at the leading terms there because that's what determines the degree, but it also makes sense that we're only thinking about the leading terms. If you remember back to the polynomials on their own, right, not in a fraction, but just polynomials on their own, we had the leading coefficient test where, depending on basically only the leading coefficient, that determined the end behavior. Well, if we have a ratio of two polynomials, it should make sense that kind of the ratios of the leading coefficients, and degrees are going to determine the end behavior. So, if I have a degree 1 divided by a degree 2, what behavior will that be? Well, let's scroll down a little bit and consult the chart. So this is at the bottom of the page, and I had a degree 1 over degree 2, which meant the degree of the bottom polynomial was higher. So that looks like I'm looking at this last category, which often we'll sort of colloquially call a bottom-heavy polynomial. And if you think about a bottom-heavy polynomial, we had x over x squared. Well, if you ignore all the other stuff that was after it, because we're thinking sort of about end behavior, we're sort of ballparking this or estimating. If you estimate this, then this would sort of have the x's cancel out and sort of turn into 1 over x. And for 1 over x, as x goes to infinity, well, we end up with 1 over big number, and 1 over a big number is going to get closer and closer to 0. So if you have a bottom-heavy polynomial, then you are guaranteed to have a horizontal asymptote at y equals 0. Because the bottom term takes over, it has more weight, and so it's going to just cause all the terms as x gets very large or very small to go towards 0. We'll come back to the test and talk about the other two options, but I want to go back to the polynomial we were graphing. We now know it's bottom-heavy, horizontal asymptote at y equals 0. So I've compared the degrees. I decided that the bottom had a higher degree. I looked at the test and confirmed that the test says I should have a horizontal asymptote y equals 0, which I can plot on the graph, and I will in a second. We can also use the notation. We say as x approaches infinity, f of x should approach 0, and as x approaches negative infinity, that's the left end, f of x should also approach 0. So just to remind us about that notation. And we can go ahead and put that on the graph. You can do a dotted line. I'm going to do a little squiggly line so it's a little easier to see. There's my horizontal asymptote. The next step in graphing a rational function is factoring all the numerators and denominators. So I'm going to go back up here and just write the factored form up here. So the top x minus 1 doesn't factor. All I'll do is keep that in parentheses to avoid any weird canceling mistakes. X squared minus 2x minus 3, that's a quadratic. Usually these, because we want you to be able to solve them in a normal amount of time, will be pretty easy to factor. Factors of minus 3 that add to minus 2 look like minus 3 and plus 1. So let's say x minus 3 and x plus 1. So I've factored the numerator and denominator. Now I'm going to reduce and find the location of any wholes. Remember from the last video that wholes are if you have a factor that cancels out. Boom, like that. Now in this polynomial, I don't have any common factors. there are no holes. But it is important to check, and this is the stage at which you would check. And if there were any holes, you would reduce, and then you would proceed on to the next steps. So now we're going to find the x-intercepts and the vertical asymptotes. To do that, we're going to look at the zeros, or which are the values that would make each zero of both the numerator and denominator. So the numerator, x minus 1, if that's 0, when would that be 0? Well, that would be 0 at x equals 1. If x equals 1, then I would have 1 minus 1 over negative 2 times 2, which would end up with 0 over negative 4. 0 over negative 4 is perfectly fine. That's just 0. So the zeros of the numerator are the x-intercepts of the graph. The zeros of the numerator are the x-intercepts of the graph, and in this case, x equals 1 is an x-intercept of the graph. And we can go ahead and plot x equals 1 as an x-intercept of the graph right on the graph right now. The zeros of the denominator are going to be the vertical asymptotes. Of the graph. Zeros of the denominator are the vertical asymptotes of the graph. Because those are the things that will cause you to have division by 0. Division by 0 is undefined. Even if we have something like 0 over 0, still undefined. So the vertical asymptotes of this graph are going to be the zeros of those terms, which would be x equals positive 3 and x equals negative 1. And we can go ahead and plot those on the graph as well. Just one note, I'm using kind of squiggly lines to show the asymptotes. That's because it's hard to read on the video. I often, if I'm doing them by hand, I'll use dotted lines to remind myself that the asymptotes are not part of the graph itself. They're just sort of the guidelines or the fences that the graph has to fit within. So going back to the process, we've done step 3, we've done step 4, we've done step 5. We're now going to plot all the horizontal and vertical asymptotes, intercepts, and holes. We did that. Now we're ready to finish sketching the graph. We've kind of set the table, we just have to fill in all the pieces. So plugging in a few more test points, then sketching the rest of the graph. So how do you choose what points to test? Well, I'd like you to think about the graph as being separated into 4 zones. And the separators between the zones, we call these boundary values or boundary points, are the asymptotes and the zeros. The reason that we consider those the boundary values is because in the factors, that's when any of those factors could potentially change from positive to negative. Factor isn't going to change from positive to negative unless it's at one of those boundary values. So the graph isn't going to go above or below the x-axis unless it hits, encounters one of those boundary values. So because I have 2 asymptotes and 1 x-intercept, that's sort of 3 things, which has cut the graph into 4 different regions. And I've shaded them here with my 4 colors of highlighter. Now I'm going to sort of just make a in-out table. So I'll say x and f of x. And I'm going to put like a dividing line at those boundary values. And then I'm going to pick a value that's not one of the boundary values to test. So negative 2 is over here. I'm going to test x equals negative 2. I'm going to test x equals 0. I'm going to test x equals positive 2. And I'm going to test x equals positive 4. Because those are all values that aren't one of the boundary values. I already know what happens at those boundary values. It's either a 0 or an asymptote. So I have to test some values that aren't among them. So here's how you test a boundary value, or you test a value. You just plug it into the equation. I like to plug into the factored form. That's usually easiest for me. And I have the factored form up in the right there. So it would be negative 2 minus 1 over negative 2 minus 3, negative 2 plus 1. And then you can simplify that further into negative 3 over negative 5 times negative 1. So altogether, that would give you a value of negative 3 over fifths over 5, because 2 of those values, negatives cancel out, but one of them stays. You had 3 total negatives. I've already worked these boundary values out ahead of time, and to keep the video short, I'm not going to show my work on all of them. But when you plug in 0, you can check that you should get positive 1 over 3. When you plug in 2, you can check that you should get negative 1 over 3. And if you plug in 4, you get positive 3 over 5. And there is some symmetry there, and I think that's just coincidental because we kind of picked a point that's 1 to the left and 1 to the right of all of our asymptote values. Now, we can plot all of those points on the graph as just further evidence of where the graph will be. So negative 3/5, and you don't have to be exact. Negative 2, negative 3/5 is a little less than negative half. So I'll plot a point right there. 1/3 at 0 would look like this. Negative 1/3 at 2 would maybe look like this. And 3/5 at 4 would be a little above 1/2 over here at 4. It turns out that that's all the evidence we need to graph this. We also actually know one other sort of secret piece of evidence, which is that when I found the x-intercepts at x equals 1, I also know that there's no more x-intercepts, so that I know that the graph can only cross at that point, and otherwise it has to stay to the top or bottom of that red line that I've drawn horizontally. So, to finish constructing the rational function, we're just going to kind of connect the dots with a smooth curve, but we have to fit between the asymptote while hitting the dots. So, on the leftmost side, we'll use blue here. On the leftmost side, you can start at that dot. To the infinity side, negative infinity side, you have to approach the horizontal asymptote. And to the right side, you have to curve down to the vertical asymptote. A lot of people ask me, how do I know that that one goes down? Well, I know that if this turned around and went up, then I would have another x-intercept. But I don't, because I know that that's the only x-intercept. So the graph cannot undo, turn around and go up, or there would be another 0, and we would have seen it in the factors. So instead, the graph must go down. Over here, we can start at the intercept and go to the left towards that asymptote. Well, again, I know it has to turn up because there's no other zeros, so it can't turn back down. And on the right, it looks like it's going down. So it's going to have this sort of like reverse cubic behavior there. Although it approaches an asymptote in which cubics don't, so it's not quite a cubic, but it's got that same kind of wiggle action. Then over here on the rightmost side, there's no other zeros, so as you approach infinity, you just have to trend towards that 0 line, and as you go backwards, remembering that the graph has to be everywhere except where the asymptotes are, it can't turn back around, it has to go up, because if it went back down, there would be another intercept, and we know there's not one. Other than the test values we plugged in, we don't, again, have a lot of evidence for specific y values. I'm not going to be picky about your specific y values. As long as you kind of get the right shape and in the right quadrants and the right positive and negative behavior, often we care more about whether the function just above the axis or below the axis, rather than the actual fraction value that it reaches. So I think this would be a pretty good graph of the function x minus 1 over x squared minus 2x minus 3. And you can plug that into Desmos to check if you would like. I'd like to go back to the bottom of this page and just look again at the test for end behavior. We already talked about the bottom-heavy test. If you have a bottom-heavy function, your horizontal asymptote will be at y equals 0. What if your function's not bottom-heavy? Well, there's two other cases. The second most common case is if you have the same degree in the numerator and denominator. So the example here is equal degrees, and you have negative 4x squared, over 2x squared. Those are the same degree. Now, if I ignored that minus 1 right here, just maybe scratched it out for a second, you could reduce this down, couldn't you? And the x squares would actually reduce out. And you would just get negative 4 over 2. And that's effectively what happens when the degrees are equal. As x approaches infinity, f of x is going to approach, but not touch, because there are these other terms over here, the ratio of the coefficients. So because the coefficients here are negative 4 over 2, I know, or you know, that the horizontal asymptote will be negative 4 over 2, which is y equals negative 2. That's what happens when the degrees are equal. We'll see an example of that later on the page. But it's a horizontal asymptote. It is going to have the same behavior to the left and right, but it's not going to be right at 0. It'll be a horizontal line somewhere else, depending on what the coefficient ratio was. The third case, and this is like the least common and also the most difficult to graph, probably outside the scope of this video, is if you have a higher power on the top. Now, if you imagine that all these other terms weren't there for a second, and you reduce this out, you would get 2x, because the x squared and x cubed would cancel out. So you would have an asymptote behavior that is y equals 2x and maybe plus some other stuff, so it wouldn't quite be exactly that line, but you would have something called a slanted asymptote, or sometimes called an oblique asymptote, or a curvilinear asymptote, depending on exactly how that worked out. Graphing these are beyond the scope of this video. Probably these two, balanced and bottom heavy, are what we're going to cover today, and those are the most important ones to know. If you do want to find oblique asymptotes, you can use long division, and we'll cover that at a later time. So now I'd like to just get into graphing some examples. I think we're going to do about 5 examples to finish this off. 3 are on the page, and I've added a couple more to show you some of the other behaviors that a function can have. I'd encourage you to pause the video and work out at least the 3 that are on this page on your own first before just watching, if you feel confident. And if you don't feel confident, then just continue watching and take some careful notes. So, first step is look at the end behavior. So we have a degree 1 over a degree 2. So this is going to have a horizontal asymptote of y equals 0 because it's bottom heavy. The degree on the bottom is more. So horizontal asymptote of y equals 0. Again, this is kind of like the last example. Now we're going to factor the numerator and denominator. Numerator's already factored. The denominator will factor into x plus 3, x minus 3. Now let's just check for holes and asymptotes. So, any holes? No, because there's no terms that cancel. No terms cancel out. Zeros. The zeros of the function are the zeros of the numerator. So the zeros of the numerator are x equals -1 from the numerator term there. And the vertical asymptotes, vertical asymptote's quite a spelling test. I would encourage you to make sure you are spelling those words correctly, by the way. Come from the zeros of the denominator, so that would be x is equal to plus or minus 3. And that comes from looking at those terms. I also have my horizontal asymptote, so I'm going to highlight that, although I already put it on the graph. And with all of that in place, we can plot most of that information on the graph already. So we had the 0 at x equals -1, make a big dot there. The vertical asymptotes were at the 3's. So I can already tell that this graph doesn't have quite the same symmetric behavior as the other graph, because the factors aren't quite as symmetric, although the asymptotes are. I also know there's no other intercept, so it's kind of time to plot points. Make some space. Just find a space around your graph. You can list out the boundary values. So the boundary values are the asymptotes and zeros. And you need to test values that are to the left and right of those boundary values. So again, the graph is broken into sort of 4 different regions that I need to test values into. So you can look at this and decide on good values to test. It looks like -4 would be a good value to test. -2. 0 is always a nice value to test just because it's easy to plug in. And 4 would be a good value to test. Now, normally you would just take a couple minutes and plug in those numbers. I don't want this video to last forever, so I've actually typed this into the calculator, and I'm going to use the table to find those. So I have this in the calculator. I'm not going to graph, though, importantly. I'm just using the table feature. So at -4, it looks like I have -0.4. Notice at -3, we have that error because that's the vertical asymptote. At -2, we have positive 0.2. At 0, we have -0.11, which is 1/9, by the way. You can look at that just from plugging in 0. And at 4, if we scroll down, so we can see the asymptote again, and then at 4 we have about 0.7. So I hope you can excuse my use of the calculator there. I'm not trying to cheat. I'm just trying to save you a little bit of time. And with those values in, we can clear out the highlighter from the graph and actually plot the points. So negative would be right around here. That's right around there. That's really close into 0. And this is a little bit higher. So again, you can just start on whichever side you want. I like to start on the left and work towards the right, but you can start in the middle and work out. It doesn't matter. To the far left, you have to approach 0 because that's the horizontal asymptote. And then this graph can't, again, bend back around because there would be another 0 there, so this graph has to turn downwards. We're going to jump over that asymptote to the middle piece. This is going to be one continuous piece between these asymptotes, unbroken, because the only way you can have a new piece or a new break is because if there's an asymptote. So starting from the 0, working to the left, you're looking like we're on the positive side, so that's going to curve up. And starting from the 0 and working right, it's going to go down like a little more, so that, again, it's not symmetric necessarily, and where exactly the turning point is doesn't quite matter, but what does matter is that eventually it does turn down and approach that asymptote. And I'd like you to put an arrow on the end of this function to show that you know it's going down that way. And then finally on the right side, you can draw the horizontal asymptote out towards infinity and connect the dots upwards to show that vertical asymptote. Remember always that your graph has to be a function, so if you find yourself trying to make a graph and it curves around, that's not allowed. That cannot be. And another error I often see is like in these middle pieces, students will plot a point and then they'll just kind of draw the graph like this. That's not acceptable. You need to show, because this looks like if it were to continue, it would go right through that asymptote, like a truck crashing through a wall, which we don't want. So you need to show that your graph is turning back down to approach that asymptote correctly and have the right behavior. And this is a pretty good graph of that function. All right, just to freeze them here, now on to the next example, which is given in factored form, so we won't have to factor this one. Sometimes they come factored, sometimes they don't. So the first step is to look at the degrees. So in this case, I can see that the numerator is degree 2, and the denominator is also degree 2. So the horizontal asymptote will be at the ratio of the coefficients. Well, it's all factored out, so the coefficients are actually just the numbers right out here. So the horizontal asymptote will be at y equals 4 over 2, which is 2. So the horizontal asymptote is going to be at y equals 2. Now it's already factored, but I do see there's a common term here, so let's reduce this out. So this is going to be 4. Actually, 4 over 2 also reduces to 2 over 1. So I'm going to just reduce that while we're going here. And then those x minus 1's terms do cross out. And so we get x plus 3 over x minus 4. But when they crossed out, that created a hole, which is the first thing in our list of things to test. Or I forget what the number was on the list, but we have a hole at x equals 1. Now we need to find the y-coordinate of that hole. You do that by plugging x equals 1 into the reduced polynomial. So we're going to do 2, 1 plus 3 over 1, 1 minus 4. So that's negative 8/3, or which is about negative 2.6 repeating. So I know there's going to be a hole at 1, negative 2.6. That's the location of the hole. Where will we're doing zeros next. So the zeros will be at x equals negative 3, because those are the zeros of the numerator. And the vertical asymptotes, which if you know how to spell it correctly, you can just write VA, are going to be at the zeros of the denominator. So that will be at x equals positive 4. Now you just go ahead and put all the holes, zeros, and asymptotes on the graph. That's the 0. There's just a single asymptote at 4. Vertical, sorry. And there's a single horizontal asymptote at 2. We also know that at x equals 1, there will be a hole at around negative 2.6. So we'll represent that with an open circle, roughly in that location. And what's nice is we can use that open circle as one of the points that we're plotting in the graph. So we're now ready to construct the graph. And I would actually argue that you don't need to do any more test values. Because if you think about what you know about the graph has to touch that 0, and so it would have to continue off and hit the asymptote there, and then it would have to continue over here, hit the hole, and then from the hole it would have to continue down to this asymptote. And then over here on the right side, people always forget that there should be another piece of the graph. We know that there's no intercepts, which means that the graph can't be anywhere down here, because if it was, say if it was looking like this, you'd have another intercept. We know that that cannot be. So my suspicion is that the graph is actually going to do this. And then hit its horizontal asymptote over off to the right. Now, I am going to plug in a couple points just to check and confirm, because that's always good to be safe. You don't want to make assumptions. So let's just make that table of values and check some points. All right, off camera, I went ahead and plugged in those values. I didn't need to plug in 1 again, but I put it on the list. I also picked 0, which gave me negative 6/4, which is around negative 1.5. So that's one more point on the graph. At negative 4, it had a value of 1/4, so I'll put that on the graph. It's kind of confirming the suspicion. And at 5, we had a value of 16, which doesn't even really fit on the graph, but it does confirm that the point is way up here. So I think that's now enough information to finish off the sketch, just to give myself a little more space. Graph has to kind of come in here, hit all those points, and then shoot off to be part of its horizontal asymptote, which will extend off this way. And on the right side, the graph has to shoot down from the top, no zeros, and then bend off and hit its horizontal asymptote over on the right. So it's probably an imperfect sketch. I'm sure the real graph looks a little bit different, but it's a pretty good sketch of what this rational function would look like. And I'm just to add here that sometimes folks get in their head like, well, we're going to plug in values anyway. Could I just start by plotting random points? The answer is absolutely not. Can you imagine if you didn't know anything about asymptotes and you just started plugging in random points? You would have like the wildest connect the dots situation ever, and it would be completely inaccurate. So don't think that you can get away with just plugging in numbers. You have to think about zeros and asymptotes and holes first, then plug in values based on those things you found. All right, let's do a problem that's like a little bit of a mix-up. What if I asked you to write a rational function with specific features? All right, so what can we do here? Well, we know we're going to need a fraction. We know that we need vertical asymptotes at x equals 1 and x equals 4. The vertical asymptotes are the zeros of the denominator, which I'll just call q of x. So I need a factor that would have 1 and 4 as zeros. So how about x minus 1 and x minus 4 here? Pause and double check that that makes sense to you. We need a 0 at x equals 2. So that's going to be a 0 of p of x. So we need an x minus 2 on the top. We need a hole at x equals 0, and it says any y-coordinate is okay. So to have a hole at x equals 0, I need to have a factor that cancels out that would make 0 here. So I need to have just a factor of x, or you can think about it as a factor of x minus 0 if it helps, on the top and bottom to create that hole. So x and x. We're building up this function piece by piece. And I know that if I was to start to graph this, I would cross those out and say there's a hole at x equals 0. But we're building the function, so we're going to undo that. And now the last part is the part that makes this like weird and confusing a little bit. We need end behavior of y is equal to 1. So right now, my end behavior would be y equals 0 because I have a degree 2 over a degree 3. So I need a way to add a degree to the top, but without adding any more zeros, because this is supposed to be the only zeros. We should say only. So how could I do that? Well, one way to do that would be to add an exponent on the x minus 2 squared, which is something you can absolutely do. That will change the shape of the graph, of course. It'll change what happens when you plug in those test points, but now you have degree 3 over degree 3, which means that the end behavior is the ratio of the coefficients, looking at that test, which is 1 over 1. So my end behavior is y equals 1 over 1. So we've now fixed this polynomial up using everything we know about the tests for functions. That would be a rational function that you know would have those properties. To close this video out, I want to do 2 more examples. I'm not going to graph these by hand, but I want to look at some weird behavior that can happen in a function like this. And hopefully looking at weird behavior will help you understand the graphs. So I wrote on the bottom of the packet that it is a myth that you can't cross an asymptote. Everyone seems to think that if you have a horizontal asymptote, and then you have a graph that goes across it, something bad has happened. And it could be that you made a mistake, but it could also very well be that the graph just does cross that asymptote. As long as it turns back around towards the end, you are absolutely allowed to cross a horizontal asymptote. You can't cross a vertical asymptote because that represents a value that's undefined. So a function will never do this. It will always bend out of the way. In that sense, vertical asymptotes are much more like walls that the function really is trying to get out of the way of and not crash into. But a horizontal asymptote is more like a magnet or something. The function just getting closer and closer to it over time. Here's an example of what that would look like, and we can look at why the factors show you that that has to happen in this function. So first, we can look at what the horizontal asymptote is. So the horizontal asymptote is based on the degrees. We have a degree 1 over a degree 2 polynomial. So the horizontal asymptote from the test on the previous page has to be y equals 0. It's bottom heavy. We have a 0. We have no holes because no terms canceled. We have a 0 of x equals 4 from the numerator. And we have 2 vertical asymptotes, one at x equals 0 from the x term, and one at x equals 2 from the x minus 2 term. And if we were going to draw the whole graph, we could put all of those things on there. We could say, here's our horizontal asymptote, here's our vertical asymptote, here's our other vertical asymptote, and then the only 0 is over here at 4. So because of that, it seems like the graph will have to do something like that and maybe something like this. But it can't cross anymore. So the graph could not do that because we can only cross right here. But because the graph has to cross right here from one side or the other, it's going to have to cross, and then it has to turn back around and approach its asymptote. It just has to. It must, because you have to approach the asymptote, but you have to cross at 0. So there's no choice but for the graph to turn around. Now let's see how right I was in my guess. So this is what Desmos says for this graph. You can see those vertical asymptotes. I guess that's in red, so we'll draw these in green. You can see those vertical asymptotes at 0 and 2. You can see the horizontal asymptote at 1. You can see the other branches of the function being either up or down, not touching the axis. And specifically, you can see right here, the function does cross at 4. And then it looks like right around at 6.28, it doesn't get very tall. At 6.28, it has a little maximum that the computer found. And then it just turns right back down and approaches 0. And it's kind of weird behavior, but it's totally allowed to happen. That's one of the strange things that can happen with rational functions. But the good news is you don't really need to know about that. If you were graphing this, if we were trying to graph this, finish this off by hand, all you would do is just make your sort of in-out table, plug in some test values, plug in -2, plug in 1, plug in 3 and plug in 5, and see where the graph is, and then connect the dots, and it would all work out. So you can cross an asymptote. Next example. In the writing of a function problem, we added an exponent to some factors, and that actually does change the graph in kind of a cool way. Remember how the graph of y equals 1 over x squared had that vertical asymptote, but then to the right and left, it was going in the same direction? That similar thing is going to happen whenever you have either whenever you have an asymptote on the bottom that has an exponent. And remember how y equals x squared, just the parabola, bounced at 0? Whenever you have a factor like a numerator on top, and you have an exponent on that factor, you're going to have a 0 that has a bouncing behavior as well. So I do have the graph prepared for you. I won't make us graph this by hand, but let's work up the graph just to take a look. So clear this out. So we have a degree 2 over a degree 3. So we're going to have a horizontal asymptote of y equals 0 because it's bottom heavy. We're going to have no holes, no factors canceled out. We're going to have a 0 at x equals -1. And we're going to have vertical asymptotes at y, the equation of the asymptotes is x equals, so they'll be at x equals -2 and x equals +1. But notice that 0 had like a multiplicity of 2 because it had an exponent of 2, and so did that asymptote, had an exponent of 2 there, so they both kind of had this multiplicity of 2. Let's just go straight to the graph and see what Desmos would say about this picture. Move that up here. We can see that it does have those vertical asymptotes that we observed. At -2, the graph is down to the left and up to the right of the asymptote. But at 1, notice that the graph is actually going up on both sides. And also, at -1 at our 0, notice how the graph hits that 0 and then kind of bounces. If you're following the graph, you hit the 0, and instead of crossing over, the graph bounces up. And that's because that 0 had a multiplicity of 2. So the sign of the graph wouldn't change there because that represents a factor that's squared. And the same thing at the asymptote. Because you have a factor that's squared, the sign of the graph won't flip from positive to negative. It's going to stay positive to the left and right of the asymptote. And again, the good news for us is that you don't actually have to think about that multiplicity thing too hard. If you were graphing this by hand, you would just make the table of values, you'd test all the boundary points, and you'd find values that correlate and connect the dots. But I just wanted to show you that as a kind of a cool feature and a way to end this video. All right, we've been talking for a long time. I would encourage you to please let me know what questions you have. Graphing rational functions is fun. It is challenging. There's a lot of tests to memorize. There's a lot of procedures to memorize. Please make sure that you come to class knowing those procedures. It will really help you in the long run. Thank you all, and have a great weekend.